All right, you're fine. All right, so we're going to be looking at number 2 and number 3 from the notes packet.
Wait, this is the notes? I thought the white was the notes.
So for an elevator, so because these problems are a little bit easier because there's not an x and y component. It's only a y component. So with this, we have let's just take a look at a situation in which the acceleration is going up. Okay. The difference is just the length of the tension force. Let's take a look at this. For the elevator, we have a gravitational force going down, and we have a tension force going up. Just like that. So, what's the next step?
The equation.
What's it called?
Newton's law.
Net force equation.
Net force running around.
Net force equals mass times acceleration. We only have one direction for this, so it'll be the y's. So the net force in the y direction equals m times a of y. What are the y forces? Tension force minus weight equals m times a of y. If it was accelerating downward, that just means that the gravitational force would be larger than your tension force, right? Oh, you guys already had that written down, didn't you?
Yeah.
Now for a constant speed. So when you see constant speed, what flag should go up in your brain?
No acceleration.
Thank you, Shui.
No.
So the acceleration is 0. You should know, you should see that, realize that. So with the 0 acceleration, we know that the forces are going to be equal and opposite here. And my vertical acceleration is 0. So I have tension force minus weight equals 0. Because remember, 0 times mass is still 0. So just to clean this up a little bit, I'll put weight on the other side. I got tension force is equal to weight. Yes?
What does that mean it's not moving?
That could be the case. Or it could be moving at a constant speed.
What if it has equal forces pulling it up and down?
That just means its speed's not changing. Remember, you can be moving at 60 miles an hour, like on the highway in your car, and we'll be moving at a constant speed, which means your net force is 0. How can your net force be 0 when you're going 60 miles an hour down the freeway?
Acceleration.
You have a force going forward from the engine, propelling you forward. What's opposing that force? Friction and air resistance. And my car has it's very aerodynamic.
Unfit.
That's right.
Yeah.
So because of that, no. Because of that, because of the aerodynamic, I get better gas mileage because the engine doesn't have to work that hard when it's going at constant speed. The less friction you have, the less the engine has to work.
Do you still get like 70 miles per
No, I get like 42 right now.
hour?
I went to do my oil change and the guy let a bunch of air on my tires.
Why?
Because you put more air in your tires, the tires are like harder and not so squishy, and you get a lot better gas mileage.
Why do you let it up? Why do you let the air out?
Because I was over like the recommended.
Yeah,
It was a rougher ride, but I was getting like 45 miles a gallon. All right, free fall. The only force acting on it would be gravity. So with our net force equation, I'd have negative Fg is equal to mass times, what's my acceleration in free fall?
0.
No, it's G.
Oh, free
Negative
fall.
9.8, right?
Sure. Do you need negatives in this? Or is it all just
We're taking care of the negatives when we write these equations out. So if the Fg points down, write it as negative Fg. Well, what would that person feel like inside the elevator?
weightless?
Smashing against the ceiling.
No, he's weightless. He'd be just like Chris Hadfield on the space station.
Wouldn't he be like pushed against the top though?
No, because he's moving. He's accelerating at the same rate which the elevator's accelerating. So they're moving together. When you fully give into gravity, you feel weightless.
That's how that plane does it, right?
But once you slam against it right away, because you're still, and then if
The elevator and you are accelerated at 9.8 meters per second squared, right?
Down.
It's not, for you to be hitting the ceiling, that means the elevator is accelerating faster than you are. Right? It's not. All objects accelerate at the same rate, so you feel weightless.
So
Can't you like jump in the elevator at a certain point?
no.
Yeah.
And then it makes you feel
Yeah, because what's happening is when you jump, and the elevator, when you're going up, yeah, when you're going up and it stops, and that moment you jump, you have inertia, and your inertia will kind of keep you going.
So if it's falling in free fall and you jump at the last second, what happens?
Nothing. You're going way too fast.
Right.
Unless you can jump at it like 30 meters a second. They do that in Mythbusters. They put like
That's why I asked.
that dummy on like a spring.
But that didn't really work out that well.
No, it got destroyed. All right, next one. Let's go to the lawnmower. I'm gonna get to this so we can get your homework out. Let's pick up the difficulty a little bit, shall we?
Well, that was hard though.
No, this is good. We're gonna get it harder now.
Yeah.
Now we're gonna be pushing and pulling at an angle. And Gabby, you know that when we push or pull at an angle, we break it into X and Y components. So if you didn't understand X and Y components last unit, learn it because it's not going away. There's like a couple of people in here that didn't know what they were doing. All right. So free body diagram. Here we go. Weight. I'm pushing it down into the right. Force applied. Normal. If it gets moving to the right, those are like motion marks. There's friction force going backwards. And since I'm at an angle with my applied force, I have a force applied X and a force applied Y. And here's my theta. Thank you, Schley, for raising your hand. Yes?
I forgot. I tried to raise my hand, but you don't call me. Do we need the motion marks or is that
No, that's just to signify that it's moving that way, so the friction is always resisting motion. Friction resists the motion. Let me zoom in a little bit on it. You think Josh is gonna watch this or not?
No.
Alright. Always start there. These will be the X's over here, and we'll do the Y's over there. So X's. Net force in the X direction is equal to M times A of X. Over here, the net force in the Y direction equals M times A of Y. Is the cart or the lawnmower flying through the air or going into the ground very fast? Is it like accelerating into the earth? No, so A of Y is 0. It's not accelerating up or accelerating down. So what are my horizontal, what are my horizontal forces? FAX, FF, and what else? That's it. FA of X minus FF equals M times A of X. I'm not done yet. I can expand FAX out. What does FAX equal to? In terms of theta.
Something cosine theta.
FA cosine theta, that's that, minus FF equals MA of X. See that? Now for what do I have for my Y's?
Why is 0?
No, my forces. FN, FG.
FA1.
Yeah, don't forget about this guy over there, that little guy. I'm gonna write this down here for more room.
Even though it equals 0.
Let's solve this for normal force. We know already that normal force determines the amount of friction, right? Right, ready?
Yeah.
Okay, friction force equals normal force times mu. So here, I'm increasing my normal force by pushing down on it. Look at what normal force is equal to. It's equal to the object's weight plus my vertical applied force. So I'm pressing the surface of the lawnmower and the surface of the ground together harder than it normally would be. Because of that, that increases the amount of friction. And so mathematically right there, Fn equals weight plus Fa wide. See that? Let's look at a situation in which we're pulling the lawnmower or whatever the object is now. Okay, so this next one, I'm pulling a cart. Let's take a look at it. Fg, Fn, I'm drawing that Fn small and I'll show you why. I'm pulling up like this. I need to break that into an x and y component. Fax, Fay, what else do I have? Ff. Huh. Write this down.
I thought this was part of the first
You're
one.
daydreaming, I don't know what you're doing.
I thought this was part of the first one.
No, there's a second one now.
Oh, okay.
I'm like leaking in, but it's the second one. So what are my equations? I'll write them down here. What do I have? Start here. X's, Y's. Net force X is MA of X. Net force Y is MA of Y. My A of Y is going to be 0. You guys, does this make sense or no?
Not really.
Why? You writing this down? So, what do we get here? We have FAX, FF. I expand this one more and say FA cosine theta minus FF. Now for the y's, what do I have? Normal, FAY, FG. Plus FAY minus FG, 0. Let's solve this for normal force and compare it to the previous problem. What's the difference?
Plus and minus.
You're subtracting now. When you pull an object like that, you're pulling it up on it, you are separating the objects a little bit. The normal force, or the force pressing the lawnmower and the ground together, is it's its weight minus your force. So that decreases friction. If you're gonna pull if you have to drag something across your yard, like you're doing yard work, pull it upwards. Don't push it downwards. Because it decreases the amount of friction, it makes it easier.
But wouldn't be harder to
I don't know.
Push it upward. That is sin theta.
Oh, sorry, yeah, sine theta. No,
No?
this would be sine theta. This would be the sine theta.
Yeah,
Yeah, we can expand that out more if we want to. I'm just comparing these. I'm comparing this and this to each other.
yeah. Okay.
Is MAX, is that mass times acceleration of X?
MAX. I'm doing your homework over the weekend.
That didn't help.
Well, Shelly, what was your question?
Is that the mass?
Yeah,
Times
mass
acceleration?
times the horizontal acceleration.